Hello everybody and welcome back to PharmaWise. This video is going to be about dynes, specifically conjugated dynes. We will be learning what are dynes, what is the classification of dynes, how they are named. Then we'll go into some structural considerations and then we'll discuss some methods of preparation for conjugated dynes. And chemical reactions I'll cover in the next video. So let's start. So first question, what are dienes? Di is for two, ines is for double bond. So whenever in a compound there are two double bonds, such compounds are referred as dienes. Now what is the categories or what is the classification of dienes? So if the double bond is adjacent to each other, see there is no any single bond in between them. So if this is the condition, such dienes are called as cumulative dienes. Next, if the double bonds are separated by one single bond between them, such double bond, single bond, double bond kind of dienes are called as conjugated dienes. And if the double bond is actually separated by more than one single bond, see here there are two double bonds separating these two, there are two single bonds separating these two double bonds. So if this is the condition that the double bonds are separated by more than one single bond, then these are referred as non-conjugated dienes, or they're also called as isolated dienes. Isolated dienes have their properties very similar to regular alkenes because the double bonds are well separated. But the conjugated dienes differ in chemical properties than our regular alkenes. Why? The answer lies in its structure. Okay, where the double bonds are separated by only one single bond. So you can see double bond, single bond, double bond pattern, which is called as conjugation. So we'll discuss about it a moment later. First, let's discuss how we are going to name these dienes. So it is very simple. As we all know, we'll be having a parent alkane, and what we do is we replace the prefix ane by ene for our regular alkenes, right? But here there are two alkene groups, two double bonds. So what we will do, we will retain this A and before ene we will put di. So what we will get is alk as our prefix, and for suffix A will be retained and we'll put dyne. So alkane is going to be my name, general name, but I have to specify the position of double bonds. So whenever there is a double bond, I will count the first carbon, the locant for first carbon of double bond, and I'll put that here, right, before diene. So I'll give you one example. Let's derive the name for this: CH2, CH, CH, CH2. What could be the name? So we have to give numbering in such a way that both the double bonds should get lowest possible locant. So here it will get the same locant even if I number from either sides, right? 1 2 3 4, 1 2 3 4. So at first carbon there is a double bond, at third carbon there is a double bond. So 1 3 are my locants and 4 carbon parent is my butane. So what will be the name for this? Buta, and before dyne I have to put the locants 1 and 3. So 1 3 dyne. This is how I will write the name, IUPAC name for this particular conjugated dyne. Okay, if you are not sure how to write the IUPAC names, what are the conventions, or you want to learn the IUPAC nomenclature in detail, I have a detailed playlist for IUPAC nomenclature. I will link it somewhere here and in the description box. Please go through it. It contains so many videos which will clear all your doubts. Okay, so moving further, what I will do for something like this: CH2 double bond CH, single bond CH2, single bond CH, double bond CH2. Now this is another compound. I want to name it. Now what I will do, now look, 1 2 3 4 5. So 1 and 4 are going to be my locants. If I number it from left hand side, same, 1 2 3 4 5. So 1 and 4 are going to be my locants from even right hand side. So 1 4. And how many carbons? 5 carbons. So penta is going to be my prefix, and 1 4, penta 1 4 dyne is going to be the name for this compound. I hope you're understanding the categories and the nomenclature for dynes. Now, as I said, the conjugated dynes are special because their chemical properties differ from other compounds. Now let's discuss why. So here the conjugated dyne I have written, and it is buta 1,3 dyne, or it is in simple words it can be said 1,3-butadiene. It can also be written 1,3-butadiene. So this compound we are going to discuss in depth. So look at the compound and tell me, this carbon contains a double bond, this carbon contains a double bond, and this carbon is also part of a double bond, this carbon is also part of a double bond. Whenever there is a double bond in the system, the carbon is sp2 hybridized. So as you can see, all 4 of them are sp2 hybridized. What is the geometry of sp2 hybridized carbon? It is trigonal planar. So it contains, 3 hybrid orbitals, sp2 hybrid orbitals, but don't forget the unhybridized p orbital lying above and below the plane. So these 3 orbitals are in the plane, and this unhybridized p orbital is above and below the plane. So what I'm going to do is I'll be drawing the structural diagram for this orbital diagram for this structure. So this carbon will form a sigma bond with this carbon and 2 sigma bonds with these 2 hydrogens. These 2 are my hydrogens. Okay, and this hybrid orbital of this carbon will overlap next orbital for this carbon. This is another carbon. Now this carbon will also have 3 hybrid orbitals and 1 unhybridized p orbital. Right, so one of these will be attached to this hydrogen and the next will be overlapping for this carbon. So here I will draw next carbon, and this next carbon is going to have unhybridized p orbital like this. Again, this will be utilized for forming a bond with next carbon with unhybridized pz, and here the hydrogens will be placed. So this is going to be the basic structure. Now you know that unhybridized p orbitals contain electrons, single electrons, and they laterally overlap to form a double bonded system. So as you can see, this is one double bond between 1 and 2. This is carbon number 1, this is carbon number 2, and then 3 and 4, they will also have a pi bond between them like this. Now what happens as these orbitals are very close together, the electrons will not remain localized to these 2 and these 2 carbons. What happens is the unhybridized p orbital on carbon number 2 and 3 has the capacity to overlap on either sides of them. So this can overlap with this as well as with this, and this can overlap with this as well as with this. So this gives rise to a bigger molecular orbital where these pi electrons, these 4 pi electrons, means 2 electron pairs, can actually freely move, right? So this electron pair does not remain confined to these 2 carbons. It is equally attracted by these 2. So these electron pairs actually experience force of attraction from all 4 carbons, and so they are part of all 4 carbons. They are delocalized over the entire molecule, and this particularly is called as delocalization. Delocalization of electrons occurs because of the tendency of unhybridized p orbitals to overlap on either sides, and this delocalization is actually responsible for rendering different properties to 1,3-butadiene than your regular alkanes. I'll tell you why. Now if you can look at this structure, you will observe there is a one double bond, single bond, double bond. Now this is a single bond, right? So for a regular single bond in alkanes, the bond length is 1.54 angstrom usually, right? But in this structure, if we measure it experimentally, it comes down to 1.48 angstrom. Why it has come down? Because this single bond is not single bond, actually it has acquired this partial double bonded character because of this delocalization. Now because of this partial double bond character, the bond length decreases, and so this single bond is not as equal to the alkane wala single bond. It is actually lesser in length than the regular alkane. So this is what happens with 1,3-butadiene or any conjugated diene because of delocalization. So I want all of you to understand this, that all of the atoms, all carbon and hydrogen atoms, they will be part of a plane, right? All of them will be comprising a single plane, but all pi electrons will be above and below the plane. So this is how the structure of 1,3-butadiene is going to look like. Now if you have understood this structure, let's move further and discuss some methods of preparation for 1,3-butadiene. Now there are I am going to discuss 4 methods of preparation here. We will start the discussion from acetylene. Okay, so I will be taking acetylene molecule as my substrate. I'll be having 2 moles of acetylene. Then I will use a reagent cuprous chloride in presence of ammonium chloride, right? Cuprous chloride and ammonium chloride, and these 2 moles of acetylene will be converted to vinyl acetylene. Now what is vinyl acetylene and how it is actually derived? I will write the structure here, you look carefully. Double bond C, single bond CH, double bond CH2. Now in the last video I have discussed allylic substitution, and there I have discussed this allylic carbon, vinylic carbon things. So what is a vinylic carbon? Is a carbon bonded to a carbon which is a part of double bonded system, or a carbon bonded directly to a sp2 hybridized carbon. So this is a carbon bonded to sp2 hybridized carbon, so this is vinylic carbon, so it is referred as vinyl acetylene. Now how it is formed, you must be wondering how this structure has been formed. So look here carefully, I will draw this for you. CH triple bond CH, this is my 1 mole of acetylene. I will draw this hydrogen like this, and another mole of acetylene I will draw like this, C triple bond CH, and this hydrogen I will draw here. Okay, now how we are going to derive this particular structure? What I'll do, the one of the bonds means 2 electrons from this triple bond will be utilized to form a bond here. Now if I form a bond here, 2 bonds will be remaining here, so this carbon becomes deficient, and as this carbon is already bonded to 4 bonds, it has already 4 bonds, it will not form this bond. So first this bond and the electrons will be transferred to this carbon. So this happens simultaneously, and so what we get is, from these triple bonds, this CH as it is, this triple bond as it is, this carbon as it is, from this triple bond 1 bond will be shifted here like this, double bond will be, this carbon bears 1 hydrogen, that will be here. Here only double bond is remaining, and this hydrogen is shifted here, so here CH2. This is how vinyl acetylene is formed. Now this vinyl acetylene we have to subject it to partial hydrogenation. Now partial hydrogenation, how we will make it work? So for partial hydrogenation we will use catalyst PDBaSO4, which we call as Lindlar's catalyst. Now Lindlar's catalyst, what it does, it actually restricts the hydrogenation at only one site. So here it actually hydrogenates this triple bonded system, and so what we'll get is, here 1 hydrogen will be added, so CH becomes CH2, triple bond will be converted to double bond, C becomes CH, and rest of the portion as it is. So as you can see, we have got 1,3-butadiene as our final product. We started from acetylene, 2 moles of acetylene. In presence of cuprous chloride and ammonium chloride, we converted them to vinyl acetylene. Vinyl acetylene, upon controlled hydrogenation in presence of Lindlar's catalyst, have resulted in formation of 1,3-butadiene, which is our required product. So this is one method of preparation for 1,3-butadiene. Let's discuss the second method. Okay, you can take a screenshot if you wish to. I will give a moment in between so that if you want, you can take a screenshot. Okay, now so the second method I'll be discussing is from 1-butene. Now from 1-butene, how we are going to derive the 1,3-butadiene? 1, 2, 3, 4. This is 1-butene, my substrate. Now what I will be doing is I'll be subjecting this to bromine in presence of very high temperature. Now you know, when we subject an alkene to very high temperature and halogen, then it definitely undergoes Allelic substitution. Okay, you should definitely check out that video of Allelic substitution. It is really helpful. Okay, so I'll link it in the description or somewhere here. So Allelic substitution happens. Now what is Allelic substitution? This is my double bonded system, and this is my carbon, allelic carbon. So I will write this bromine, that bromine will go and substitute here. So what I will get is C, Br, C double bond C. Okay, this is what we are going to get. Now what we will do, we want 1,3-butadiene. Now what we have to do is we will be removing HBr from here. So that will be called as dehydrohalogenation. Dehydrohalogenation. And dehydrohalogenation is effected in presence of alcoholic KOH. We have to heat it in presence of alcoholic KOH. So hydrogen from this carbon and bromine from this carbon will be removed, like HBr will be removed, and a double bond will be created here. So what we will get? C double bond C, single bond C double bond C. Nothing but 1,3-butadiene. Okay, hydrogens you can put. So when we started from 1-butene, we subjected it to reaction with bromine in high temperature Allelic substitution. We got substituted product that we subjected to dehydrohalogenation in presence of alcoholic KOH to get 1,3-butadiene. This is the second method. The third method is actually very simple. What we will do, we'll start with 1, 2, 3, 4 and OH here. So we will start with butane 1,2-diol, right? Butane 1,4, butane 1,4-diol. And what we will do, we will remove hydrogen and OH from adjacent carbons. So if we remove water molecules, it will be dehydration. This dehydration can be effected in the presence of acid catalyst. So it is called as acid catalyzed dehydration. So after acid catalyzed dehydration, these water molecules will be removed, these two bonds will be removed. So a double bond will be created here and here. So what I will get? C double bond C, single bond C double bond C. 1,3-butadiene. So by acid catalyzed dehydration of 1,4-butane-diol, we can get 1,3-butadiene, which is our conjugated dyne, right? There is one more method I want to discuss. Let's do dehydration of plain alkane. That can also give us conjugated dyne. So 1, 2, 3, 4. This is my N-butane, and N-butane on hydrogenation, dehydrogenation means I will remove hydrogen. Now for removal of hydrogen, I have to use an oxidizing agent, right? So what I will use? Chromium oxide in presence of aluminium oxide at 600 degrees Celsius. So this is catalytic dehydrogenation. So upon catalytic dehydrogenation, my N-butane will lose the hydrogens from adjacent carbons and they will develop double bonds here. So H2, 2 moles of H2 will be lost, and what we will get is C double bond C, single bond C double bond C. So 1,3-butadiene. So I hope you are understanding. We have discussed in total 4 methods of preparation. First, from acetylene to vinyl acetylene to use of Lindlar catalyst, and we got 1,3-butadiene. Second, from 1-butene, next from 1,4-butanediol, and next from N-butane. Just remember the reagents and the methods which we have used. I hope you have understood. Now chemical reactions are also very significant, and there is one very important chemical reaction of conjugated dynes, which is Diels-Alder reaction. So I'll cover all the chemical reactions in the next video. So you till then you just subscribe to the channel and stay tuned with PharmaWise. Keep studying, keep rocking. Take care. Bye bye.